This problem introduces the idea of a skew heap and asks us to recover permutations of insertions that could have produced the given skew heap. Here you see the construction process of a skew heap. Given a tree, our task is to determine both the minimum and maximum permutation that could have formed it under the skew heap insertion. Here we have a different skew heap being constructed. A skew heap satisfies the heap property where every node's value is less than or equal to the values of its children. However, unlike a normal binary heap, skew heaps impose no balancing constraints. When inserting a value into a skew heap, one of two things happen. If the root value is less than the new value, we swap the root's children and recursively insert into the new left child. If the root value is greater than or equal to the new value, then the new value becomes the new root, and the entire existing heap becomes its left child. Let's use a tree to build some intuition. Here, we insert a permutation of 8 numbers. For simplicity, when the root is less than the new value, instead of swapping the children first, we go down the right child and make all our swaps at the end of the permutation. Watch how the tree changes as we insert values greater than or equal to the root and less than the root. For tree problems, it helps to focus on the root. The root is always the minimum value in this heap, and it appears at some position x in the permutation. Because trees are recursive, understanding what happens at the root can often tell us a lot about what happens in the entire permutation. At the root, we can have two subtrees, L and R. Since the root's value is the global minimum, when the root was inserted, the entire previous heap became its left child. Every later insertion is larger than the root by the minimum property, so all of them trigger a child swap at the root, meaning that new nodes will alternate between the left and right subtrees. Because these insertions alternate right-left, and because all earlier values were placed into one subtree, we can kind of deduce the root's insertion index from the sizes of the left and right subtrees. Let's examine this a little more closely. We know that the largest subtree must start as the left subtree when the root was inserted, and every subsequent insertion forces a swap of the children of the root. This means that every subsequent insertion will swap the largest subtree with the smaller subtree, meaning that the largest subtree switches sides from RL, RL, RL for every insertion after the root. This gives us 3 cases. 1, the left subtree is larger than the right subtree. 2, the right subtree is larger than the left subtree. And 3, the left and right subtrees are the same size. When the size of the left subtree is larger than the size of the right, we know that we inserted an even number of nodes after we inserted the root. This is because the largest subtree must start as the left subtree, and for the left subtree to remain the largest, we must swap an even number of times. Since the number of nodes inserted after is even, we know that there is an equal number of nodes inserted after the subtree into the left and right subtrees. Let's call this number y. Then we know also that the size of the right subtree is y, and that the size of the left subtree is the position of the root plus y. This implies that position of the root is the size of the left subtree minus the size of the right subtree. On the other hand, when the size of the right subtree is greater than the size of the left, we know that we have an odd number of nodes inserted after the root. To make the right subtree the largest, we must swap it in from the start, and we must swap an odd number of times since our largest subtree started on the left. Since the number of nodes inserted after is odd, we know that the left has one more of these after nodes inserted than the right. Let's call this number inserted into the left y. Then we know that the size of the left subtree is y, and the size of the right subtree is the position of the root plus y minus 1. This implies that the position of the root is the size of the right subtree minus the size of the left subtree plus 1. When the subtree sizes are equal, we have a special case. Since we are alternating insertions after the root, the number of nodes inserted to either side could be equal or it could differ by 1. In both of these instances, there exists a construction that keeps the size of the subtree equal. The first one puts the root at the start of the permutation and then alternates between right and left, putting an equal number of nodes into each subtree. The second construction puts the root at the second position and then alternates between left and right, putting one more node into the left than the right. Note that these are the only two possible constructions that keep the subtree sizes equal, as if we put two nodes at the start of our permutation, then since the alternating pattern can only reduce this difference by at most 1, our difference at the end must be at least 1. To summarize, we can determine the position of the root given the two sizes of the subtrees. We can use the following control sequence. If the left subtree size is greater, the position of the root is equal to the left subtree size minus the right subtree size. The difference number of L's at the start, then the root, then RL alternation. If the left subtree size is less than the right subtree size, then the position of the root equals the right subtree size minus the left subtree size plus 1. If they're equal, the position of the root is either going to be 0 or 1. Now, given the sizes of the left and right subtrees, we can have covered all cases, found that we can always find the minimum and maximum location of the root in the permutation. I claim this actually solves our problem. We noticed that we not only figured out the position of the root, but we also figured out which positions belong to the left subtree and which positions belong to the right subtree. Therefore, we can separate out the permutation into left subtree and right subtree, solve the permutations on the smaller subtrees, and then merge them together given the ordering we got to restore our final permutation. In the subtree sizes are equal case, since we have two possible constructions of root positions, we can just choose the smaller position in the minimum permutation case and the larger position in the maximum permutation case. Before moving on, let's take a quick detour to talk about a technique known as small to large merging. This is a technique used to efficiently merge n separate sets into one final set, where we are restricted to only merging two sets at a time into a singular set. This is often used in data structures such as the disjoint set. Formally, you repeatedly take two sets at a time, taking all elements of the smaller set and adding them into the larger set. In a lot of problems, we don't actually have control over which sets get merged, just that we have the ability to control how we want to merge the two sets. This gives us a technique to efficiently merge n sets together, regardless of the order in which we chose the sets. At first glance, always merging the smaller set seems like O of n squared, as we need n-1 merges to merge n sets, and each one is bounded by O of n. However, let's follow the path of a singular element. We can show that by only ever merging the smaller sets into the larger sets, we will always double the size of the set this element is a part of at every step. And that means that we can only double the size of its set at most O of log n times until we hit our size of n. Therefore, this element must be part of a smaller set at most log n times, and so it will be part of at most log n merges. The total number of operations we do will then be bounded by O of n log n, provided we always merge the smaller set into the larger set in O of small operations. Returning back to our problem, we wish to merge the left and right subtrees into a single permutation. Let's look at the case where the left subtree is greater again. The other cases should be similar. The key is that here we want to merge the 5 elements in the left subtree and the 2 elements in the right subtree into the permutation. First 3 elements are left, then the root, then the right element, left element, and alternating after that. I claim that we can actually do this merge in O of small time. We can pop out the elements of the left subtree that occurred before the root and save them into a temporary list. Then we can add the root into the list and add the elements of the right list and temporary left list alternatingly into the final left list. This takes O of small because the size of the left elements after the root alternates with the size of the right subtree, so it's bounded by the number of elements in the right subtree. Given this, we can make a final sketch of our solution, and then we can go code this up.